asymptomatic people infected with COVID-19. By definition, they don't have any symptoms. So we are not supposed to tell the difference between them and the healthy. What if I tell you AI is able to tell the difference by just listening to the way they cough? Would you believe that? It sounds magical. In fact, humans cannot tell any difference. But the system that is built by an MIT team can detect it with 97% accuracy. That's interesting. In this video, I'm gonna to explain how they do it. By the way, I make deep learning explained video every week. So if you would like to receive more relevant videos like this, don't forget to subscribe. And your subscription is also my best encouragement to make more videos like this. So here are the highlights of this paper. COVID-19 cough test is non-invasive and it's basically free because most people have phones. And more importantly, it's real time. You can get your test results almost instantly. Just need to run through the model and it's pretty fast. And it's very important that you got your test result as soon as possible. The interval between doing test and getting result is troublesome. So that's the advantage of this cough test. And one caveat, this test is by no means to replace PCR test, but it's an excellent tool for you to do the pre-screening at scale. And let's look at the model. The model is basically a classifier. It uses the CNN-based model to analyze the cough audio and draw the conclusion of how likely this person get COVID. And let's look at the performance side. It has 98.5% sensitivity. The sensitivity is recall. So means if the group of people that you test, there are 100 people constructed COVID, and this tool is able to identify 98.5% of that, which is really, really high. It has 94% specificity. That means the true negatives will be 94% accurate for the true negative. And the label for this data is on PCR, which is the most accurate form of COVID test. It's based on this true label. And more importantly, it has 100% recall on asymptomatic cases, which means if there are 100 asymptomatic cases in your test group, you will be able to identify all of them. Comes with some false positive, but all of them will be recalled. And let's look at the use cases. It's especially good at nationwide screening. If you pay attention to news, some countries, they actually want to or is doing nationwide screening, which is do the test for every single citizen, every single resident. But that will be very, very difficult in terms of logistic and cost. And this tool is cheap and fast. So it's kind of a really good candidate for that. And you also can monitor the outbreak, and more importantly, you can do the very high scale test and identify which group you really want to go with PCR test. And this work is done by MIT and is published the Engineering in Medicine and the Biology IEEE journal. And there are multiple clinical trials in hospitals. Looks promising. So let's look at let's take a closer look to this paper. Basically the advantage of this paper is to detect the asymptomatic COVID infection. And the assumption of the paper is asymptomatic patients doesn't mean they are truly asymptomatic. They are still some changes happen in their body. This is assumption. But this change may be too subtle for human to spot. Okay, so their assumption is the way they cough will be different. Maybe you have one question: how could they cough if they don't have any symptom? So the recall of coughing is false. So means even you don't really cough, but you will need to do the cough sound in the recording, like these things. So it's false cough recording. And this kind of cough is basically indistinguishable to humans. Means there's a person who's in asymptomatic, and there's another person who doesn't have any COVID. And you listen to their cough, you will not be able to listen to any differences between them, which makes sense. But deep learning model is able to tell the difference. Let's see how. Okay, so before they can train a model, they need to collect the data. And how they collect the data is to build a website that allow you to open with your mobile phone, with your browser on your desktop, and you record your first cough. You just cough 3 times, then you finish the recording. And they started building this database in April 2020, and they spent around a month to collect the data. And the data is actually labeled with the outcome of medical diagnosis, and which means if you recall now, then later later you kind of diagnosed with COVID-19, you will upload your result to the system, then they'll have data. If you diagnose this positive or negative, they kind of things. And they also log a lot more information about symptoms, about demographics, that kind of things. And their data sets end up having 2,660 COVID positive with 10 times more negative cases, which makes sense. A lot of test results are negatives. Okay, then they randomly select the same number of positive cases as their training set. Means they have 15% positive and 50% negative cases in their training data. And the training data is audio with label. These are results positive or negative. Before we dive into model architecture, let me ask you one question. If you are going to solve this problem, well, how would you solve it? I think the most naive way is just to use the model architecture they usually use in ASR and the tutorial, and let the model to learn end to end. We have the audio, then we have the label. But unfortunately, it will probably not work because the data points is just not enough. There's just 500 examples. If you just throw the deep learning model, let it learn fully end to end, they will be pretty hard. And that's why you need the good representation and probably some feature engineering. And in this paper, there's actually they've used some assumption and the feature engineering to make the model work. Okay, so let's see. There are actually 4 modules here. There are 3 CNN-based biomarkers, and this is biomarker models. And there are 3 CNN models accounts for different kind of assumption and pre-train on different data. And one is to let's assume that sentiment is an important thing to differentiate COVID patient and the non-COVID patient. And there's long respiratory tract. The assumption is they will change. I want to make sure that. And another is a vocal cord. Your vocal cords will also change. And before that, they actually did the process with this general biomarker, is a muscular biomarker, to model your degradation of muscle. So that's the process. And after that, after this Poisson mask, you will have the process signal of that. Then feed it to these 3 CNN models. Then after that, you have three vectors to present your result, and you concatenate that and fit into the dense layer with a ReLU activation function, and after that you fit into a sigmoid function, and you have the result here. And more importantly, they also come out a way to make this model explainable. This is super fun, super interesting way. Oh, by the way, before you feed into your raw audio, you will do the MFCC conversion. This basically, you can see this Fourier transform is widely used in the signal processing area. Okay, so let me just throw you one question. What if today I don't want to use MFCC? I want to use the word-to vector. I want to use the wave-to vector, which is a good way to represent human speech. It's pre-trained on a lot of audio files, and it achieves quite a good result. If I just use that to represent my feature, and I don't use this feature engineering at all, how will the result come? It will probably work better than the total training from scratch end-to-end model. But will it be comparable to this model? Contain a lot of domain knowledge? I don't know, but maybe if you fit 1 million data points, the result will change. So that's probably good for future work. But the most important thing is now it works, and it works on a very small amount of data. That's the beauty of this paper. Okay, so let's look at the first biomarker, the biomarker one, muscular degradation. There are a lot of prior research talking about these things. There's generally a lot of degradation can be modeled with Poisson distribution. So that's why they want to use a Poisson distribution to model the muscular degradation. And so the task of this module is to module a signal with Poisson distribution. After you apply your signal to the Poisson distribution here, Poisson decay here, which can be written here, then your signal will be more meaningful. And I'm surely don't know the full detail of this. They contain a few papers, which I don't have time to read yet. But it's a way to model muscle fatigue and degradation features of your muscle. And there are a lot of previous papers about this. You can read that if you are interested. And if you remove this biomarker one, then your error rate will just be double. So this is a transformation layer. It's not a model. There's no training process involved at all. Okay, so another module is biomarker 2 to model your vocal cords. Your vocal cords is the place that you use to pronounce any sounds, and from your throat to your mouth. And their assumption is lung diseases will change your vocal cords, which will make your pronunciation, your speech a little bit different. So they train a model. They can identify this wake word, this word. Yeah, and I just train this model first. It's a wake word model, just like when you use Alexa, you say Alexa, or you use iPhone, you say Siri. You just identify one word and one word only, and use this word to model use this model to model your vocal cords changes. And how they do that is they basically train a CNN model on these words. And there are some details about this training, which is a little bit confusing, I find. If you are more interested and want to understand more, check out the paper. So basically, this is a CNN-based model. They train on this wake word first, then they assemble this back to their big model. You can see this kind of a pre-training, and they also do the fine-tuning. Okay, so the biomarker 2 is this. The biomarker 3 is sentiment model. The assumption is if you constructed COVID, then your sentiment will change. There are some previous research about this. So that they want to train a sentiment analysis model, the speech classifier. You give the speech, you give the audio file, then the model will tell you what kind of sentiment status you are in. And they train this model on 8 different sentiment labels: neutral, calm, happy, sad, angry, fearful, disgust, and surprised. And they hope this module will help their general prediction of COVID. And they have the ablation test on how important this module is, which is not that important actually. Okay, the last biomarker is lungs and the respiratory tract, which is from your lung to your respiratory. It's different from your vocal tract. And the change of this respiratory tract and the lung structural change will affect certain things. So the assumption is your lung structure will change if you construct the COVID. So your cough sounds will change as well. And this cough sound test actually already was used for pneumonia and asthma test. So it's not like the first thing they invented. It's already a lot of previous research papers about this. So I would say it's more promising. Makes this paper more promising. Because previously I didn't even know this. When I first saw this paper, I couldn't even believe that the model can tell the difference from just listening the cough audio, right? Because even human cannot tell. So this is a rare case that human cannot do, but the model can do. Okay, so they pre-train this. The interesting thing is how they do this. So they basically pre-train this model. They train this module on the mother tongue prediction. How they do that is they have a lot of cough audio, and they have a label. If this person is a English native speaker or is a Spanish English speaker, so they have a lot of these labels. Then just let the models listen this cough, and model need to predict their mother tongue. So they do this kind of training for this module, biomarker 4. And biomarker 4 achieves 86% accuracy on this prediction, which is quite high. Imagine you can tell the person's mother tongue from listening to their coughing. It's almost unbelievable for me. But they use this to train a model. This module will help the prediction. And they will kind of model the lungs and the respiratory changes. Definitely, you need to fine tune. If you don't fine tune, this model cannot tell you anything. So, the audio will be processed by MFCC layer. Then you will have basically 1 to 4 coughs. And first layer will go through another transformation, which is Poisson mask. You change your distribution. It's like some assumption of muscular degradation. And then you go through 3 independent CNN models to model different things. One is vocal cords and the lung respiratory tract and the sentiment. And all of them receive the signal of the transferred processed audios. And then you have representations of your audio, then concatenate of them, fit them into another feed-forward neural network. Then you will get a result, which is a binary classification, positive or negative. And they also come up with, which I don't know how they do that, is the salience map, which you can interpret why model predict this and how confident model is. Yeah, saliency map. And this is the breakdown result. The hit means recall here. Okay, so we can see that the number of patients of tested COVID positive is around 2,660. And the recall of that is 94%. And for the negative cases, the recall of that is lower. Means this model tend to have the higher recall on the positive cases, which makes sense because the nature of the needs of test. Okay, so in general, the recall for these two categories, positives and the negative, is 86, which is impressive. And this is a breakdown by symptoms. There are many different symptoms. For example, fever, tiredness, sore throat, many different. And also, something like difficulty breathing, chest pain, diarrhea, cough, and no symptoms. And no symptoms official, which is like you are asymptomatic. They diagnosed by official institution like clinics, hospitals. And for the no symptom group, it has 100% recall, which is really, really interesting. And for the symptoms, if you have symptoms, its recall is just much lower, especially when the patient has diarrhea, and the recall for this is just not really great. And this is a percentage of the patients they have these symptoms. And in their data set, very few people are asymptomatic, which makes sense because if you are really asymptomatic, you don't really have any symptoms, it's less likely that you will really go test for COVID, right? But for the negative one, there are a lot of people are asymptomatic, which makes sense because they don't really have COVID. Okay, so this is the results. Very interesting, very detailed. And let's just see how some analysis of the model. And this graph shows how many layers you need to fine tune in order to beat the baseline. Baseline model is the same model, has the same model architecture, exactly same model architecture. Just the baseline model is not pre-trained on these three data sets. These three models, sub-models, are not pre-trained at all. So that's baseline model. This is a comparison how many layers you need to fine-tune to be the baseline model. The baseline model just train end-to-end on the data they have, the task-specific data, which is around 5,000. It's around 5,000. And the model they pre-train is pre-trained on a lot more data sets, 3 different data sets for they 3 different CNN models, respectively. Okay, so after you pre-train that, you still need to fine-tune to increase the performance, right? And how many layers you need to fine-tune, we can see from this. So this is like if we consider the whole model, 3 modules together, if you don't fine-tune, your accuracy is just 50%, which is just like random, to be honest, just like random. But if you fine-tune 5 layers for each module, then your accuracy will increase drastically to around 65. Then if you fine-tune 10 layers, then you will be around 70% accuracy. And if you fine-tune all layers, just fine-tune all parameters in those CNN models, the accuracy will be 86 on all categories. And this is the vocal cord model to model your vocal cord. And this also obviously, if you only need to fine-tune 5 layers to be the baseline. And for the whole model, you also only need to fine-tune 5 layers to be the baseline. And in the lung and respiratory model, the same. But the sentiment model is like, if you only fine-tune 5 layers, it's still worse than the baseline. It's just better you just don't pre-train on the sentiment data. So that tells us a lot. Maybe the sentiment data just not good for the pre-training, and or it's not really relevant to predicting COVID-19 patients' sentiment. But the sentiment module still somehow it works, but you need to fine-tune on the downstream task a lot. And this model does not only do the prediction, but also gives you the salience map, which will explain why it makes such prediction. It's awesome. I don't know how they do that, but let's just analyze this graph a little bit. So there are 3 areas in this graph. One is sensory stream, which means how it makes the prediction. Is it because of the vocal cords? Is it because of the sentiment, or muscular degradation? Which one? Or the respiratory tract? So it just shows you how it makes the prediction. Like in this prediction, it shows like it's likely that it's because of respiratory tracts. There's something that happened to these patients' respiratory tracts and the lung structure that makes the model make this prediction. And also, this is this area, brain OS, means how much confidence the model have when you only have the 1 cough, and 2 coughs, 3 coughs, 4 coughs. And you can see the confidence level increase a lot when the coughs increase. Okay, makes sense. When you have more data, you make a more confident prediction. And another area is symbolic compositional. Okay, so there are just the voting confidence and salience vector, and this is the OVBM prediction. It's just how likely this person is contracted COVID-19. Okay, so this is how we interpret this, and I think this is important. Explainability is important, especially for the medical use cases. For example, if you want to integrate this to hospitals, and when you do the prediction, this person is contracted with COVID-19, then they will ask why he's contracted, right? Why he or she is contracted. If you couldn't give the reasons, like explain why, then the doctors may not trust this system. So give them this kind of explanation is the way to gain people's trust. This is the way this can be used. Look at what we learned today. This model detects COVID via coughs. You just need to listen those recording of forced coughs. Then we'll be able to do quite an accurate prediction for COVID-19. It has 98.5% sensitivities and 94.2% specificity. And more importantly, it has 100% detection rate for asymptomatic infections. And it's super important for detecting asymptomatic, in my opinion. And it's literally free, rapid, and you get the results really fast. And it can be distributed really fast once it's approved. I think this is a super cool way to, super interesting way to apply machine learning in the real world. And it's super helpful for the situations that we are facing now. Yeah, and that's the end of today's video. I hope you enjoy it. If you have any questions or other thoughts, feel free to leave it in the comment section below. If you enjoyed the video, give it a like and don't forget to subscribe for more relevant deep learning videos like this. And other than that, take care. Until next time.